So we will speak about the novo assembly, genome assembly today. And let me just start directly by comparing the two main assembly approaches you can choose if you want to recreate a whole genome from your next generation sequencing data. So the main two approaches is the de novo assembly, when you don't have anything, any knowledge, previous knowledge. And the other one is the reference genome-based realignment, when you have a reference genome and you are realigning your short read sequences to that. So if you do the de novo sequencing, it's always complete, which means that the de novo assembler uses up all the reads, all the sequence reads you have, and put together contigs from these short reads. It will be also unique in terms of even if you are sequencing a very well-known bacterium, E. coli, probably it will be a few SNPs different from anything else in the world. So actually you are making a new, completely novel whole genome. And this is mainly this is the main aim when you are doing de novo sequence assembly, that you want to build up something from scratch. You want to build up something as a novel thing. The realignment is a different approach, when you actually want to compare things to each other, compare things to reference sequence. So even if you are compared two new genome sequencings to each other, you usually don't compare directly them to each other, but you are comparing them to the reference sequence, reference genome, and then check the differences between the two comparisons. So it is always a reference-driven approach. There are different constraints you have to think about when you are choosing the approach. The genome size and complexity is, I think, the most important. So even if you would be happy to do de novo genome assembly from human genomes every time you are sequencing a human genome, it's not really what you would do. I mean, a human genome is so big, it's so complex. So if we are just simply speaking about short read Illumina next generation sequencing, then I think the reasonable size threshold or size limit is somewhere around the very simple eukaryotic organisms, like single cell organisms. But as soon as you are going up in complexity, the genomes are too big to easily put together with de novo assembly. Of course, there are de novo assemblies for these genomes, but those are much more sophisticated. The other thing is the genome flexibility. As soon as you know that you are working with something which is known in some ways, but you are assuming some kind of extra thing in the genome. Just simply think about bacterial genomes. There are so many mobile genetic elements, so many rearrangements can happen. These are all those things that if you have a novel, completely novel gene or a gene cassette in your Staphylococcus aureus genome, you cannot really do a reference-based realignment, because those things will not align to reference because they are not there. So you can easily miss genes. So as soon as you are working with something which is much more flexible, I think the first choice is always de novo assembly. Of course, there are methodological constraints as well. If you have your long read sequencing ready in your lab and you can use it, it's much easier, much better to do de novo assembly, for example, even if you are going up to a bigger genome and more complex genome. If you have your resources and this methodological background is together with the next point, the money and time, then you can really do de novo assembly on anything. Of course, if we are just speaking about purely de novo assembly or purely reference genome based realignment, these are the two extremities, but there are, of course, alternatives, or you can complement one with the other in de novo assemblies, and we will discuss this later today. In de novo assembly, you can introduce reference genomes or reference genome contigs to help the assembler to build up the genome. And in the reference based realignment, you can ask the realigner to collect those short reads into a file that were not aligned. So if you think about my previous example where you have a bacterial genome and you have a novel region that is not present in your reference genome, there will be a lot of reads that will not align to your reference sequence. You can just simply collect these short reads into a separate file and then try to assemble them separately after. So again, when do we use usually the de novo assembly? I don't think I will speak about when do we use the realignment, because we will have the reference-based realignment on our next meeting on Thursday. So I think the prokaryotic genome assembly is almost always de novo assembly, but again, many times we are doing both. So if you just got back your clonal sequencing from the sequencing service, the first thing you should do is what we will do today is a very simple pipeline for de novo genome assembly, and then at the end you will have your collection of contigs, your assembly. But later maybe you will have hundreds of isolates, and you want to compare them, for example, by using SNP. And SNP is one of those tools which are using a reference genome-based alignment. So there, in that case, you are using one reference genome, you are comparing all of your isolates to that, and then define the distance between these. Of course, if you are facing with something unknown, so if you're just capturing something out of your sample, but you don't have any idea what is that, you have to go with the de novo assembly path, because you don't know what kind of reference sequence you can use. I mean, you can use a collection of reference sequences always, but it's much easier in small genomes to do the de novo assembly. Of course, if you have even smaller genomes like any virus or plasmid or phages, then the de novo assembly is absolutely the obvious and first choice. In metagenomics, we always do de novo assembly because, as you know, there are so many unknown prokaryotic genomes or prokaryotic species in metagenomic samples in mixed communities. So if you introduce any reference sequences to the metagenomics assembly, then you can introduce bias and you can assemble those genomes better that are known. So that's a kind of bias you don't really want to introduce. Of course, if you have unknown eukaryotic genome, you have to do, again, so if it's unknown, you have to do de novo assembly. And also there are many times when even human genomes or mouse or any farm animal genomes are resequenced because there are newer techniques. There is ever someone with a way much more money and a much more depth, higher depth, PEG biosequencing, for example, and releasing an even better quality genome, whole genome, for large eukaryotic genomes is also coming from de novo assembly usually. Before we go into the theory of the de novo assembly, I just want to make sure that all of these definitions are known to everyone. I guess that most of the people who are working in the big lab, this is just very boring, but there are other people here as well. And we will use these definitions very often. So that's why I think it's good to memorize what is what. So when I ever say about say short reads, it's always sequence read or sequence read pair from a next generation sequencing, mostly Illumina sequencing. If you are speaking about contigs, this is actually a kind of abbreviation of continuous DNA sequence. And the most important thing in contigs that contigs are always they can only contain A, C, G, and T. So that means that it's always a nucleotide sequence. There is no gap. There is no unknown part. The next level is the scaffold. So when you try to put together your contigs in that kind of organization, what you think is true. So you don't really have to define many times what is connecting two contigs together. Maybe you cannot really extract this information from your sequencing, but maybe there is some kind of residual information on how they are oriented to each other. Maybe this is coming from a reference-based refinement, or just one of the a few read pairs are bridging between two contigs. And that's when you are doing a scaffold, which looks something like this here. So you have the contig sequence 1, and then a bunch of ends, and the contig sequence 2 and contig sequence 3. So from this, you can at least know that within the genome, contig 1 is closer to contig 2 than contig 3, which can be interesting in some instances. So the assembly, the next thing, the assembly is always a collection of contigs or scaffolds in a multi-FASTA file. If you are doing a single genome sequencing or a single clone sequencing, of course, then the result of your de novo assembly is already your final assembly. But actually, we will speak about this, I think, today, if we will have time, that even if you think that you picked up one colony, especially if you are trying to culture something from a mixed bacterial community, and the colony borders or boundaries are not extremely well defined, or something is growing under the other colony, then you can pick up two at the same time, and then you can sequence it, and you can end up with 2 or 3 genomes in one FASTA file. In that case, if you have a suspicion, for example, because you see that the file size is much bigger than what you expected, then you can try to split these final multi-FASTA files into smaller assemblies. The CC and clade is not extremely important at the moment, because this is only about when we will go further and comparing different assemblies to each other. This is just remained here from another slide. So what's the main theory behind the de novo assembly? So you have a bunch, millions of short read sequences, which is here and with this blue line, and the assembler starting with a lot of different short reads, slicing the short reads into even shorter parts called k-mers. These are the k-mers. These are usually starting from 20, 22 nucleotides and go even up. It can go up to more than 100 base pairs or bases usually. So it splits to different sizes of k-mers, your short read, and we'll check all the other short reads if they have a similar k-mer in them, and if yes, then this will be a connection between these two short reads in a huge graph. And in an ideal situation, it will find quite a lot of other short reads that are overlapping nicely, for example, with the 3' end of your sequence. Maybe there can be this green one is representing a non-real alignment, because it's just aligning with a very short part. Maybe this is something which in 20 bases, it is homologous with your short read. But if you would check a longer part of this green, it wouldn't align. So that's why usually they are using multiple k-mers and multiple comparisons and choosing those ones, probably some kind of probability calculations, which is the most probable extension of each short reads. And if it finds it, especially if it finds more than one, then just simply extend the sequence and then start back again, chopping up the end of this, looking for overlapping short reads, and continue building up the contig up to the point when it realizes that the next sequence, what I would be able to extend, is actually at the beginning of my sequence, because we are speaking about prokaryotic genomes at the moment, which are circular genomes. And as soon as it realizes that I'm within the same genome or within the same molecule I started, it just finishes and you have the complete genome. This is the theory. Of course, it never works. It never works. The main problem is that you have multi-copy genes, you have transposons, you have phage sequences, and all other mobile genetic or other genetic elements that are incorporated into the genome. And they are acting as gap makers. Let me just check anyone else having issues logging into the server. Let me check if I can. I am logged in, and there is someone else who logged in as well. I think it's working. Yes, it's working. We will see it a bit later when we will log in together. We will wait for everyone, and if there is some problem with someone, then we will try to troubleshoot. Okay, so here what you can see is there is a blue line, one part of your genome, and then it continues to another part of your genome. And within the blue, so blue lines are always unique sequences, and this will be nicely extended. But the red sequence here is exactly the same as the red sequence here, because it's just a multiple copy gene or a transposon sequence. As you can see, the reads are not able to go through the whole red sequence. So if you would have a long read from here up to here, then it's not a problem, because you can see that, okay, this is going into this repeat sequence from here, and it will go out here. But because you don't have this kind of bridge, when the assembler extending this part and going into this gene or this region, it won't know where to go out. It doesn't know how to continue from this point. Is it continue? Should it continue here or here? So instead of guessing and making artificial or failed contigs and assemblies, the de novo assembler just simply said, okay, I will cut the contig here. I will finish the contig here at this point. I will start a new contig and put all these reads together with these reads, actually. And this is a new one. So it will stop the contig here. It will use all the reads that are aligning to your repeat region to build up this contig, and then it will continue to this contig, and then these contigs will be separated as well. So that's why if you do a very standard Illumina short read sequencing colony sequencings, even if you only have just one genome, just one bacteria in your extract, and you are just sequencing one genome, you will never have only one contig at the end of your assembly. It is quite variable how many contigs you can have. Sometimes it's 30, sometimes it's 80 or 100 contigs, and this will represent your genome. Of course, if you want, you can go after those contigs that were the bad guys, the repeat ones, because you will have a quite uniform coverage on those regions that are single copy regions. So the coverage will be around X. Of course, there will be a kind of normal distribution and a variation around an average value. But those that are multi-copy genes will have 2x or 3x or multiple times coverage compared to your main coverage values. Of course, there are techniques to make less fragmented genomes. As I told you before, if you have a nice long read sequencing, you can just simply bridge these fragments easily. The long read sequencing nowadays is usually PacBio or Oxford nanopore sequencing. You can cheat a little bit with Illumina. Oh, this is Illumina, not Illumina, but Illumina short read sequencing. So just imagine if you are doing parent sequencing and you are working with two different library sizes. So you are doing one library size, which, for example, will create something like this two reads here as a pair, so with a very small insert size. But you can also make a much bigger library. And if you have a read pair, which one of them is this one, and the other one is this one, then you can give a hint to the assembler how to bridge this gap and what is actually the next contig after this one and this one here. So that's also working. Of course, it's all of these things. And of course, the proximity ligation is working. When we are speaking about high C, we always say that the high C is very good because it can cross-link the genome with the plasmid inside the cell. But actually, the high C or free C proximity ligation assays have a very strong distance dependency. So you will see way much more proximity ligation events in close sequence proximity. So it's very easy to imagine that this point is within the cell, just in the 3D space, is not too far from this point, and then you will have a 3C crosslink between this point, and you will sequence one read from here and one read from there, and then you can have a guess about the proximity of these two contigs to each other, or this contig to this one, which is probably much further away. But again, all of these techniques are requiring more money, even if you are just doing multiple library Illumina sequencing, they are requiring more money. And it's always a question if you really need that, if you really want to make a perfect one contig genome. I think if you have a very interesting pathogenic bacteria, what you want to publish as a beautiful, perfect assembly and reference genome, I think in that case it is good to go up to the long read sequencing. But otherwise, if you just want to screen hundreds of isolates for specific genes, or if you want to compare them, it's perfectly enough just to do assemblies with multiple contigs. Even if you have 100 contigs within, you will be able to align them to each other, find the genes within them. It's not a problem. Okay, so we will soon go and do the real assembly on the server. So let's see what are the main things we will do today and what are the very simple steps of a de novo sequencing assembly pipeline. Of course, you can make this a bit more sophisticated and introduce extra steps here and there, but I think this is a very good starting point if you want to do colony assembly. So there are really some pre-assembly checks. The first thing we will check is that the downloaded file we are working with is that file what we want to work with. It's especially good if you get back your own sequencing. If you download sequencing from the European Nucleotide Archive, for example, or the NCBI, you don't always have the chance to check the MD5 sum. But if you are sending your Illumina sequencing to a sequencing service, they always send you back the FASTQ files, and together with the FASTQ files, the MD5 sums. You will see what is this soon. The next thing, so this is just a file check, file integrity check. The next thing is a content check, what we will do with FASTQC. So this is actually checking the average quality of your sequencing, and at this point you can decide not to go further away because you think you are just having a crappy sequencing. The next thing will be so the FASTQC is just give you a kind of big snapshot of your all of your FASTQ reads. The quality filtering is a next step when you are filtering out those reads what you think you don't need. And then there is a step when we merge overlapping reads. So if you are working with a library, sequencing library size that is not too far from the length of your sequencing pairs together, and there is a very good chance that within your sequencing library, which is again something with a Gaussian distribution probably, then you will have sequence reads that are overlapping in the middle, and then you can just merge them and get single reads, but single longer reads. The next step is the assembly, which we will do with spades, and then if we'll have time, we will do the post-assembly with starting with taxonomic identification by using checkm, and also mesh, which is two different approaches. If we don't have time, I will speak about the approaches, and we will just do it sometime next meeting, because they are very important actually. And also we will see if we can do some assembly quality check as well with checkm. Okay, so I will stop sharing this now, and I will ask someone. Okay, let's check if everyone can log in first. If no, then please tell me. So I'm logged in already, and I see that there are many other people logged in too. Gotthard, can you log in now?
Yes, I'm just getting
okay.
authentication methods available. This is no supported authentication methods available.
I can't really hear you.
Okay, I'm sorry.
Okay, so you are now logging in from Windows, I think. and using PuTTY. Okay. So you have to use that key, one of those keys, and the one which was called as a PuTTY key. Have you ever logged in before? So were you able to log in before successfully? So maybe you just have to set up the login again. So just because maybe it wasn't saved, the session wasn't saved well. Right, that's what I can imagine. Also, if you have your WinSCP set up, I think the WinSCP has a terminal window as well. So maybe if the WinSCP is working well, if you check and you can see that that's for the file transfer. If it's working well, then as far as I remember, I cannot check because I don't have Windows here now. But as far as I remember, there is a small icon somewhere in the header below the menu bar where you can open a terminal. And I think if you open a terminal from the WinSCP, it's using the WinSCP authentication method. But it's not a big problem if you cannot log in now. Just follow me, and you can do it anytime. Actually, what we will do today, I think we will be able to do a few things together in parallel, but there will be certain tasks that we cannot do together just simply because we don't have enough resources. That's especially the spades. But I will tell you how to do the assembly, how to use the spades, and I'm asking you just to log in anytime else and at least do one of these assemblies just to see how it is working. I think if we would like to run it now, first of all, it would run for maybe a half hour or an hour, and that's what we don't want to wait. And the second thing is that just one run would use up all the memory and all the CPU. So I think it's not really doable. But what I can do is show how to use. You just okay, thanks. So okay, now I will share let me share my whole screen because we will do some Google as well. Can I choose Rhiannon? Rhiannon, can I choose you to help me with the installations? No. Okay, Ibrahim?
Yeah.
Okay, I just need at least one people, but I only use Ibrahim very first. I will never use him again, I promise. I will just randomly pick someone else next time. Okay, so the reason why I need, okay. Rhiannon is back. Okay, so maybe Rhiannon will be busy on the phone later. So let's just stick with Ibrahim next time, or this time, and next time I will ask you, Rhiannon. Okay. So if you are ready, then you can do it.
I don't mind whoever. Apologies for that. Typical. Literally, they just phoned me. They're only on for like 2 minutes. But I was
okay.
like,
Okay. Then please, because Ibrahim already know how to do these things. So
okay. Yeah, I don't mind. Yeah.
Okay.
Sorry. Yeah, sorry about that. Typical.
Are you logged in, Rhiannon?
Yes, I'm logged in.
Sure.
Yeah.
Perfect. Okay. So you can do the same thing, and I will ask Rhiannon to do the installations only. So please don't do any of you, especially if you are logged into the test server, because as soon as Rhiannon installs the program for us, and everyone can use it. That's why we only use one username at the moment. Of course, if you are working on your own server, please do it. What we do. So let's start looking at the files we have. So if you, okay, I'm sharing my screen. And I will share like this now. So I'm logged in, and if I'm logged in, I'm you are usually in your yeah, it was the problem last time that the button wasn't visible, so I will just put it here like this. So you are in your home directory. Of course, I'm usually logged in with the Ubuntu user, because if there is a need to install anything with system administrator rights, then I can do it. But you are all logged in with the bioinf user. That's why there are many bioinf users logged in. That's very nice. So the first thing is that we will go to the Scratch directory, cd Scratch, where I can see already that there are some user folders, which is very nice. And also there is a raw data folder there. So if you are going into the raw data folder, then we can see one of Ibrahim's recent sequencing output files. It's a pair of sequencing files. So this is usually what you get. Oh, it's actually not Ibrahim's file. It was downloaded from a collaborator's work, as far as I know. So anyway, it's a prokaryotic, it's a bacterial genome sequencing, colony sequencing. So we are expecting one genome only in it. And there are two FASTQ files. Both of them have the GZ extension. As you can see, the GZ means that both of them are zipped, which means that you cannot really look into it. So if you want to look into, don't do this. But if you want to look into, I'll just look in the first 10 lines, then it's not really human readable because it's compressed. Before we uncompress it, let me just show you the very first task we will do, which is the MD5 sum check. As you can see, there is a third file here called 22 for blah 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 MD5 sums txt. This is a text file, so we can look into it. And there are only 2 lines in this file. There is a string of numbers and letters here, followed by the file name of the first file, and there's another string here, followed by the file name of the second file. So this is a kind of magic what you can do with MD5 hash. I'm really honest to you. I don't really know how the whole thing is done. But what you can do, even if you have a whole genome, like a whole human genome, and you make a hash, MD5 hash, and then you just change one single nucleotide in that genome, and you again make an MD5 hash about that genome, it will be different. So this string will be different if you have one nucleotide difference in 3 billion nucleotides. You cannot really go back and find out what was the original from this, but you can see if the original thing has changed. And this is what you want to see, because it can happen that during the download, you have some kind of problem with downloading. The server on the other side is too busy, or your internet connection drops, and you just see that there is a FASTQ file there. You don't really see the size, because if you say ls minus LH to see the size, the 2 files are different, which is not because they should be exactly the same, because this is a parent sequencing, which means that there has to be the same amount of sequencing reads in one than in 2, because each has a pair in the other one. But because they are gzipped, they are compressed, the compression rate wasn't the same, and that's why they are, at this moment, they are different in size. So how can we check if these MD5 sums are okay? It's very, very easy. You just simply say MD5 sum, and this is a Linux command, which is always there. So this is a completely default command that is installed together with the a Linux operating system. I can imagine that it's also on a Mac. Let me just check. Yeah, on a Mac there is something called MD5 Sum Lite. I guess it's the same kind of thing, but I won't check it now. So just you just say MD5 sum minus C, because that's how you check it, and then the file name, the txt file name, which contains the MD5 sums. So the program will go into the file, take the MD5 hash, check the file name. It will create the MD5 hash from the whole file and compare it to those things what is inside this txt file. Of course, you get this txt file again from the service. So what they do when they finish with the sequencing files, they are making these MD5 sums. You are downloading both of them. Downloading the txt file, of course, is always much safer because it's just a few bytes. There's a much lower chance that there will be a failure downloading a small txt file than a huge several megabytes or gigabytes file. So they did the MD5 sums, you download it, you do the MD5 sums again and compare them. And if they are okay, then the download was successful. So you just simply say MD5 sum minus C and then the file name and hit enter. Of course, all of you can do this. This is not just for Rhiannon, because it's not an installation yet. So as you can see, this is what you want to see as a result, that it's okay and okay. I think if I, let me just do something nasty here. I will rename the first one to a temporary file. I will then rename it back. And I will copy the second file. The name of the first one. So now we have the two parent sequencings, but actually this one is exactly the same file as this one. And this is the old first mate. So this is not really what the MD5 sum was made before. So if I run again the MD5 sum check, it will give me an error. It will give a failure because that MD5 sum, which is in the txt file, is not matching with the MD5 sum of this one. Let me just quickly put back everything. Okay. All right. The next thing what we will do is we will install FastQC and check the quality of our sequencing reads. So let's just quickly Google FastQC, and this is what I asked from you, Rhiannon, as well, because we will do the installations. I think it's the very first thing. Oh, it's actually done in the Babram Institute, so it's not too far from us. And download now, I think. Let's see if this is, oh yeah, FastQC. And here, we want to download the one which is the Linux, Windows and Linux zip file. I don't click on it because I think if I click, it's already the file. So I just right click and copy link. And we are going back to our home directory. So just say cd, and this will jump back to your home directory. And let's just simply download what we have here. Yeah, it is actually the link to the file. Do you have the same, Rhiannon?
Yeah, I'm just, sorry, I just put in the apostrophes in.
Okay.
I thought it might do it automatically.
It's a very small file, so it will download instantly.
Yeah.
And what we will do now, because it's also zip, so if you say ls, you will have much more files than I have here, but you have the zip file there, and I think we have an unzip. We don't have an unzip. We have an unzip now. Yeah. So what you have to do is just say unzip and the fast QC zip file. And this will make you a folder called fastqc. So now all of us have this fastqc folder. I have it in my home directory, and all of you have it in your /home/bioinf directory. And we only have to check how to use this. I think it's extremely simple to use. Probably just have to say fastqc and then we won't see the tutorial video. Okay, let's just yeah, so as you can see, this is probably the executable we will have to run, the fastqc. But it's not executable yet. Let me just... if you have something like this downloaded, so this is a bit more complicated than just simply installing something with Conda. So now we have to find out how to start using it. And usually there is a README file, which is there because it's good to read it. The txt file. There will be a lot of very important information here. But what we want to see is how to run it. And we won't be able to see it from here. Mm-hmm. Okay, let's see the install txt file. Let's do the one which we can. I think we will have to install some kind of Java or Java runtime environment, but it's not a problem. I can also easily install it. Yeah, I think I have to do this. And as soon as we have, okay, so here we have the how you can run fastqc. There is an interactive graphical way what we don't do. And there is this is the pipeline way how we can do. And it's just simply saying fastqc and then the txt files or the fastq files. But first I have to install the Java runtime environment. This will take a little while, I think, but it's not too long. Oh, it's actually quite fast. Okay, so this is again what I did. I installed something as a super user. That's why you always see this sudo. So this is what Rhiannon cannot do, but she doesn't have to do, because what I'm doing now, I'm installing a program centrally. So from now, all of us will have the Java runtime environment. So I think if I'm now running the fastqc, probably there will be like a minus help or something. Yeah, and it's working. So this is how we have to run it. So as you can see, it's just simply saying fastqc and then the sequencing file 1, 2, and so on. There are some extra information here, but we don't really want to. Yeah, we don't need them at the moment. So let's go back to the Scratch directory. And I ask everyone to go into their own directories. If you don't have your own directory, just make your own mkdir. Make mine. I have mine already. So I'm just going into my folder, which is almost empty. So now what all of us will do, we will run the fastqc from the same place. Did you do the chmod, Rhiannon? Do you have it in green? Let me just check. Are you here, Rhiannon?
Sorry, I've forgotten I was muted. Apologies. No, I haven't got the chmod.
Okay, so what you have to do, go back to your home folder by saying cd and say chmod. This is when we will put that executable from the executable program.
Hello, sorry, that just cut out. Sorry, you said chmod and then you said this is, and then it cut out. Sorry.
So this will put the executable flag on the program, so we will be able to execute it, and all of you will be able to. So we have to say u plus x, which means that you are adding the executable flag to the user, which is the bioinf user, and then you have to give the file name, which is within the fastqc directory called fastqc. So the same as on my screen.
Yep.
And if this is done, then you can just say here fastqc minus help. So this should work. This thing here.
Yep. Yeah.
Okay. So again, this is almost always what you have to do when you get back your sequencing files, but in few cases, the service provider already do a fastqc for you. So if I'm going on the HPC, for example, oh my God. I just want to show you something, how we get back our metagenomic sequencing data, for example. There will be a lot of files here, but as you can see, here we have here we have a pair of files with the MD5 sums. So this is already something we got back from the sequencing service, but we also have a FASTQ zip. I think it is for a whole lane, I think, usually, or so there are many cases when you already get back the results of the fastqc. I don't want to look at this now because we want to look at our own data. So now you can go your Scratch directory and onto. I don't know if you already have your own directory in the /scratch and just go into that one. So we will run the program from the home directory. We will input the sequence file from the raw data folder, and we will do the output here. Maybe there will be a -O. Yeah, we will use the -O flag and define a temporary output folder. So what you have to do is, first you have to call the program because it is not in your path yet. So you cannot just simply say fastqc because it's not there. Oh, actually we can install fastqc essentially as well. It's good to know that there is a Linux package for fastqc, but it's not there yet, but it is in your home directory. So what you have to say is, first you have to give the whole path to the program, which is /home/bioinf for you. For me, it's /home/ubuntu and fastqc and fastqc. Before pushing enter, this is the first thing. So this is how you call the program, and we will say -O and say just temp, which means that it will create a temp directory here where you are, so within your own directory. And then you have to give the path to your sequencing raw data. I guess it's okay if it's a GZ file. If not, then I will unzip it. We will see. So how you can go to the raw data folder. You can do two things here. You can say it is in the main Scratch directory. So if you have the slash in the beginning, like here or here, this is always referring to a folder which is in the root folder of your Linux machine. So the home directory is one of the main directories. The Scratch directory is one of the main directories. And if I say something that is here, then I don't put the slash before. Okay, so it's in the Scratch main directory, /raw data /something _1. So this will be the file name. This is one of the methods you can put the full path to the file. The other way is that you are giving a relative path. You know that if you are in your own directory now, in your Scratch directory, then you have to go up one and then go into the raw data directory. So going up one in Linux language is .. This means that let's go up. So this is now in the Scratch directory. Within the Scratch, I would like to go into the raw data, and I would like to analyze this file. Let's just first analyze the first one, and let me start it, because if it fails, then I have to unzip it. Okay, the specified directory is not exist, so you have to make your directory as well, mkdir10. Otherwise, it's working. So if you make your own directory, you can do the same what I did, and let's just run it, and let's bring out everything from the server we can. I will check in a different window how much do we use the server, just to be curious. Oh yeah, JY is running already. So if you look at the CPU now, all of the CPUs are used. So we are slowing down each other, of course, but it's not a problem. Mine is finished, and I hope most of yours will finish soon as well. And I can, of course, luckily I can see if it's finished. I will wait until all of your runs will finish. There's only one.
Laish, would you mind showing the code again? Sorry, I
So
was
you have
being
to
very
make
slow.
you have to make the output directory before.
Yeah, so I
starting
did the
or-
temp. I just did the temp directory, but I delete the code, and now I don't remember what was the code.
Okay, sorry, it is here.
Oh, it's there. Okay, thanks.
Lajos, when I run that, I got permission denied.
Are you in your own directory?
Yes, I am.
The question is, it is denied to write into the temp directory. I'm sure that there is no problem reading the file. I guess there is no problem running the fastqc because everyone else can run it, and you are logged in with the same username. What if you just simply go up and try again? Because maybe there was someone else opened the file as well, and maybe that was some kind of collision between two processes. Or just use the up arrow, and then you can run again. Is it permission denied again?
Yes, it's denied again.
Okay, do you have the temp directory like this here in your folder, having all the permissions RWX, RWX? But of course, having I can actually see it. Oh, you don't have a temp directory? Someone is working in the main Scratch directory, not in the I think that was maybe you. Can you go into your directory? There is no subdirectory in your main directory, so you just have to go into your directory and make the temp there. There is no temp directory there yet.
So what do you see? I don't have a home directory there.
So if you are in a Scratch main directory, you have to go into the JQ.
Yeah.
Okay, like cd JQ.
Mm-hmm.
And if you are there, you have to make your temp directory mkdir temp, which I don't want to do because I am not.
All right. Yeah. Let me try again.
And if you are there in your JQ directory and you have your temp directory there, then you can run the command. I'm pretty sure. Mm-hmm.
I run that again. It's the same. Permission denied.
And you are in your JQ
Yes, I mean the
directory.
Yeah.
And you are running this here, the same thing
Yes.
you have here.
Exactly. Yeah.
This is strange. Okay, let's just
Yeah, it doesn't matter. You can, yeah.
yeah, let's go along and we will see later because
Yeah,
yeah, probably there's something a small problem here or there. What you will be able to do, you can just simply download the same results from anyone else's directory because you will log in with the bioinf user as well. So if I'm going to my own directory now, what I can see in the temp directory is that we have this HTML file, and this is what we will need. Of course, this is only the results of our first FASTQ file, not the second. If you want to run later, you can just do the same thing for the for the mate pair. And when you are doing your own data analysis, of course, you want to see the quality of all your FASTQ files, but in this case, this example is enough. So I will go up on the file transfer, which is, in my case, this is the CyberDuck, but you can do it with FileZilla, you can do it WinSCP, anything, and you should go into your main root directory, and within the root, you have to find the scratch. Within the scratch, your directory, and from the temp directory, just copy the HTML file, not the zip, just the HTML somewhere. Yeah, I will just copy it to my desktop. And as soon as you have the HTML file, it is a form of like a website, so you can open it with any kind of web browser. So what I will do, it will look something like this. So I will do it with Safari. I will just simply go to the desktop and find this 224 blah 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 HTML and open it. And this is the result of the FastQC. So
sorry, I got a bit lost. So I just opened the temp file on my directory, and I see the HTML file. Do I copy that to my desktop?
Yeah, you have to copy it to your own computer now, because we can't really see the graphical things on the server.
Okay.
Yeah. So just simply drag and drop to your computer and open it by double clicking on it or by opening any kind of web browser.
Sorry, Lyash, I'm being a moron. How can I get to that page? Sorry, to get the file.
So so do you have the HTML file, or do you have a problem? Okay, so
No,
first
sorry,
so you have to use the file transfer program that I mentioned in the email, which is, if you have a Mac, it's probably the CyberDuck. So something like this. I don't know if you can see my desktop now, or so the CyberDuck, and in the CyberDuck you have to open the connection. If you already opened the connection before and it is saved, it will be in your history. And you just have to double click on the 128.232.226.61 IP address, and if you have it, you can simply browse the server, and you have to go up to the root directory, which is the // go into the scratch, go into your own directory, go into the temp, and copy and paste the HTML file.
Okay. Yeah.
But if you don't have the file transfer, it's not a problem, because you can just see what we are doing, and you can do this anytime.
No, I have it. I just can't remember the password. I just need to go back and find my details to get into it.
Yeah,
so.
there shouldn't be any password.
Okay.
Okay, so the first thing what you want to see is this graph here. Back in like 5-10 years ago, it was very, very different what you saw. So what you see here now, let me check, there is a question. Solved, okay, thank you. So before, like a few years ago, what you saw here was a huge drop down at the end, because when pyrosequencing was quite new, the quality of the end of the sequencing was usually quite bad. The beginning wasn't bad, but what you see here is that even together with the I think this is probably the 95% confidence interval, the top and bottom, or maybe the minimum and maximum, I don't know. Probably it's just a confidence interval. But as you can see, the whole sequencing data is within the green range. So if you see something like this, then probably you don't really need to do any special quality filtering. We will do one thing, which I think it's good to do just right after this step. But if you see something like this, then you don't have any problem with your sequencing data. You can go down and you can see if there was any problem within the on the lane. So this is usually a heat map, which gives you a quality distribution physically on the sequencing chip. Because what you don't really want to see here is a bright yellowish, reddish line somewhere in one position. Because that means that you have a bad sequencing quality because there was something bad on the chip. So probably within a physical space of a chip, there was something wrong on the lane. But this, if it's blue like this, but usually this line is coupled with something glitchy here as well, because then you have bad reads. This is again just a distribution of the qualities. As you can see, most of our base pairs are within a very good range. Usually, as you can see up here, if it's above 28 or 30, that's the most common threshold for a very good quality, but also above 20 it is acceptable. And as you can see here, actually the whole x-axis is starting around 20, which means that maybe there are a few reads with acceptable, but most of the reads are good in quality. Most of the bases, these are I think nucleotide based. This is just about how the different nucleotides are represented within different positions. I think maybe in the beginning we have some kind of adapter maybe, but I don't think so. The GC content is perfectly okay. Again, here if you see more than one peak, then you can be suspicious that maybe there are some mixture in your sequencing. So for example, if you have two different species with two different GC content, then and they were sequenced with quite similar proportion, then you can easily see two peaks here representing the two different GC content of the two genomes, or maybe there is a shoulder somewhere. There isn't any N, so that's good. This is the not sequenced thing. The sequence length is always the same. That's not a problem. There are some duplication, so that's good, because then we can deduplicate it, and that's the next step what we will do. There is no Illumina adapter, so in total the sequencing is perfect, which is what you would expect nowadays from a next generation sequencing. But as you saw, there are some duplicates. Duplication can come from two things. When you are making your next generation sequencing library, you are doing a few PCR cycles, and you can just simply sequence exactly the same PCR product twice. Of course, you don't really want to have it twice, because it doesn't give you an extra information. You have to be, of course, very careful with this, with duplications, because we are now doing genome assembly. If it's genome assembly, you don't need to quantify the reads. As soon as you are going to RNA-seq, you cannot just simply bin or throw away the duplicates, because the duplication can come from real biological reasons, just because one transcript is represented with a much higher abundance, so you will have much more reads from that transcript. But when you are doing DNA sequencing, and especially when you are doing de novo sequencing, de novo assembly, then you are trying to minimize the input data to the best quality and non-duplicated reads. If you are introducing more reads, you will need more time, more memory, and more CPU time to do the assembly. And you don't give more data to the assembly. So our next task is to deduplicate the FASTQ reads. And as I said, one duplication reason is the PCR, but there's also another one. So the pyrosequencing is actually happening on these flow cells, within the flow cells. And what the Illumina sequencing machine detects is light. As soon as a nucleotide is incorporated, it will emit a specific wavelength light. And this is what is detected by the machine, and this is how it builds up the sequence. If there is a sequencing failure in a physical point of the chip, of the flow cell, but there is a good sequencing right next to it, then the machine can detect the sequencing and the light from another point, which is right next to the detection point physically, which means that it will detect the same kind of pattern, sequence pattern, that is physically right next to a good sequencing. And again, this will create just a simple duplicate, but this will be an optical, not a PCR duplicate. Luckily, these physical coordinates are encoded into the FASTQ files. So let me just show you. I don't know. I think almost all of you saw a FASTQ file already, but let me just go through what is in the FASTQ file. Is there anyone who haven't seen a FASTQ file yet? How it looks like? Do you want me to give a very short description how the FASTQ file looks like?
It's always good, so then we know that we haven't seen it the right way, I guess.
Okay. So let's go back to the rotator. I will just show it on my screen, so you don't have to do this now. So what I will do, I want to keep the zipped files, so I will just simply copy one of the zip files, number 1, to a temporary file. And it is not, it's not having the gz yet, but it is also gzipped. So I can just say gunzip. I'm using gunzip and not unzip, or gunzip, not unzip here. So the way how we downloaded FastQC, we downloaded in a zipped file, which is compressed with the zip compressor, and this is compressed with the gzip compressor, which can be uncompressed by the gunzip uncompress command. Sorry if it's very confusing. It was very confusing for me when I started doing things like that. But what you have to remember is that if it's gz, then you can unzip with gunzip. If it's .zip, then you can unzip with simply just saying unzip and not gunzip. So I will unzip a temp FQ. I knew that will happen. This will be very fast, I hope. I will try to expand my window because I think I will need the whole width. So let's just look at the first 10 lines of this FASTQ file. So what you have here is one FASTQ record, one sequence record always has 4 lines. So when you look at the FASTQ file, it is always in 4-line sections. This is the first one. This is the second one here. And this is the first 2 lines of the third short read. In the first line, which is always starting with this @ sign, we have some instrument identifier and probably the barcode or something like that for the flow cell itself. But most importantly, we have the coordinates here. This is, I think, one of the coordinates, and this is the other one. Or probably this is the same. So maybe this is also just a flow cell or the lane identifier. And these are the 2 coordinates here. So from these 2 numbers, the next program we will use knows that this one is very close to this one or not. Actually, they are very far from each other. So this is the first line. The second line is always the sequence. You sometimes have a space and another information here about the indexes, sequencing indexes. But we don't have it now. So this is the sequence itself. This line is usually empty, starting with a plus sign. The plus sign is always there, but it's usually completely empty. In this case, they are just copied the content of the very first line. So it's exactly the same. This line is having the same data as this one, which is completely unnecessary. And this line is the quality score. And luckily, we have a quality score where the first quality is an @ sign. And this is very important because in FASTQ files, you cannot extract the file if you are going through the FASTQ file, for example, with a program. You cannot say, okay, all the lines that are starting with an @ sign will be the ID line. We'll have the identification of the position of that sequence read. Because as you can see, this one starts with an @ sign as well. But in this case, this is already a quality. This is the quality of the first G. And this is the quality of the second G. And this is the quality of the C, and so on. So each nucleotide has its own quality score. Why it is not simply from 0 to 9? The problem with 0 to 9 is that it's only a scale of 10. So if you want to make a more highly detailed quality score, then you have to use letters. And in this case, it is not just letters, but also other signs. It's, if you want, you can go after this just by Googling the Phred score. And then you can see what is this Phred score actually, how it looks like. Not here, probably on the Illumina site. I actually found it before. Yeah, I think this is a good example. I think we are using the 33 one. So you can see here that in the first column, the Q is the quality. And in the last column, this is that kind of character they are using. So of course, these are the low quality scores, and it goes up to 42. No, this is not, I think, the one we are using at the moment, but actually it's not important now. I don't think it goes up to K. I think nowadays it just goes up to E or F. But as you can see, the capital letters means usually a very good quality. But even the @ sign is 31. As I mentioned before, above 28, everything is perfect. But above 20, which is the number 5, everything is acceptable. So in this case, all of these characters are representing very good sequencing. Actually, we have J. Maybe it goes up to K. Just don't have that perfect sequencing. So that's how the FASTQ file looks like. Always 4 lines. If you want to process your own FASTQ files, you always have to process it line by line and say, okay, I'm in the first line, I'm having the ID. I'm in the second line, I'm having the sequence. I'm in the third line, I don't have anything, and I'm not really care about it. And I'm in the fourth line, I have the quality scores. And from this, you can calculate an average quality score. So you can just translate all these characters to numbers by using this table. So you will have that amount of number as the length of the sequence, and you just simply make an average from them, and you will have an average quality for that read. And for example, that's a way how you can exclude reads if they are bad in average quality. Right. So time is flying. So let's go and do the application, and maybe we will have a bit time for doing the flash as well. So Rhiannon, again, I will ask you to go back to your home directory by saying cd. And what we are Googling is the bbmap programming package. So just simply Google bbmap and go to the bbmap download, which is the SourceForge link.
Is that the file that we will use for the replicate, right?
This is the one which will, so the bbmap package is a huge package. I have never had the time to go through. I mean, it contains, I think, more than 100 different scripts. You can do a lot of things with bbmap, even align reads. So it was written especially to work with next generation sequencing data, and I really hope that sometimes in my life I will have time to go through it. But we will only use one sub part of it, which is the clumpify, which we use to deduplicate our reads. So instead of yeah, let's push the big green download button. But it will again download to your own computer. If you click on the problems loading, then you can just simply have the direct link here, and then say right click and copy link. Are you having it, Rhiannon?
I'm just on the bit where it says direct link. So we're just copying the link there. Yeah.
Copy the link. I hope you are already back in your home directory. If no, just say cd.
Yep,
And
right.
then we are doing the same type of wget, and then paste the whole thing here. Use the apostrophes because there are so many strange characters inside this URL.
Yep.
And download it. Wow. This is a bit slower, it seems. It's only me and Rhiannon who has to do this. Of course, again, because this is just a one-time installation, what we will do. Surprisingly slow.
Yeah, mine's at about the same percentage as yours.
Sorry that we have to wait. So just going back to why it is downloading, going back to the FastQC. When you see something like this here, what we get first when I try to run Java here, not Java, but FastQC, or much more something like this. So if you see an error message like this, that means that the program you try to run is written in Java programming language. Is it Java or Java?
Java.
Java. Okay. Sorry.
I don't think it really matters. I don't think it really matters. I mean, it's not English, is it? So I guess you can say what you want.
Okay. So it is written in Java, and you have to download the specific runtime environment, which is usually this this GRA or JRA you have to download. But of course, you won't have to do it on this server anymore because I installed it centrally. The BBmap is a bit simpler because the BBmap is was written in Python, I think, most of it. And Python is usually a default programming language that is installed together with the Linux operating system. Also I think on the Mac, the Python is there usually. Perl as well, always there. This is the most fascinating part of bioinformatics, waiting for the program to download. It's actually just 10 megabytes, so it's not a big one. Probably there is some problem on the SourceForge server. I don't think there is a download speed problem on this server because this is sitting inside the university server park, which is, I'm sure that it is connected with the fiber optics to the outside world. Maybe the GTA 5 is on the SourceForge as well. I don't know if you heard, if you are gamers like my friends, that the GTA 5 game is free to download.
Ooh, done.
It's done. So the problem is that because we have this awful file name, if you say ls now, we have this awful thing there. So let's just quickly rename it. So what we do is mv, and then I think just write in a capital B and then push tab.
Yeah.
And then just say bb map, just simply bbmap.tar.gz. Okay. So this is when we are renaming a file, moving from this long file name to a very short file name.
Yeah, that should be okay.
Okay, so if it's done, then you will have the nice red bbmap.tar.gz there.
Yeah.
So again, what we have here is having two extensions. It is tar and gz. The gz means the same thing as we saw with the sequencing data. So it is compressed with the gzip algorithm. But there's also something else, the tar. So if I'm just simply saying now, and don't do this with me at the moment, Rhiannon, please.
Mm-hmm.
So if I just simply say gunzip bbmap, what it does, it is uncompressing, but what I have is the tar file here. This is not what I want. This is not the collection of the scripts. This is just one file, which is unusable like this. The tar is a program that you can use to make one file from many, many small files. It is very useful if you want, for example, if you want to make your program package to be downloaded easily, because you just have to put up one file and provide it for downloading, and people can download it, and then they can unpack it. The difference between the gz and tar is that tar doesn't do any compression. It's just put all the files together into one big file. So if I'm now going back and gzip back my map, so I have the same bbmap.tar.gz now, we can uncompress and untar in one step. And this is something what you should maybe write down, because you will face with so many tar.gz files. There are so many times when the data is coming in tar.gz. There are so many times when you have your program package in tar.gz. So the only thing you have to do is just simply say tar. This is the program that will unpack it. And this is, again, always part of every Linux distribution. -x VZF, which means these are all options. You can say -x VZF, or you can say -x -v -z and -f. but you can just simply put them together. It's much easier. The X means that you want to extract. So you want to unpack your file. The V is just say that it will be verbose, so you will see what is happening. If you don't want, you don't have to. The Z is there because it is gzipped as well, so it is unzipping and then unpackaging the things. And the F is only means that there will be a file name here following this option. And the file name is, of course, the bbmap.tar.gz. Okay, so this is how you always untar and unzip all the tar.gz files. I'm pretty sure that you will meet this tar.gz many times in the future, even if we will have time today. And we will have, I think the next program we will use has the same tar.gz. Okay, and if you push enter, you will see that there is a lot of things unpacked. And these are all unpacked into the bbmap directory. So luckily, if you say ls, what you have here as a new thing is a blue bbmap folder in the home directory. We can do a little bit of cleanup just before we are filling up our home directory. So Rhiannon, you can also just remove the bbmap tar.gz and the fastqc.zip. We don't need them anymore because we have the unpacked folders here. Okay. If you list the bbmap, I mean, yeah, this is just a huge amount of green sh and py. No, it's actually sh, but I think there is something else. It's not bash script. If you see .sh, then it can be a bash script, but I'm not really sure that it is a bash script. Okay. So what we will do now, let's speed up the things. Let's go back to our sketch. Only we have to go back to our own Scratch directory. And first, just simply run our clumpify from here. So what we are doing is /home/bioinf for you. And now this should be done for all of us, not just for Rhiannon, but everyone, please do this. bbmap and clumpify, CLU, and then tab.sh. If you just simply run this, then you will get back the a kind of help. This is almost always working with scripts. If you don't get back the main help, then maybe you have to say -h or -h or -- help or something like this. But usually it is working like this. And the basic usage is here and the very top. So it is, you are using the same thing what we wrote here, but you are then writing in the input file and the output file, and then the thing what you want to do. So even the clumpify can do more than one thing, but we only want to use it for the duplication. And we also want to do it together, the two files. So instead of using in equals to something and out equals to something, we will use this here. So as you can see, there is an in equals and in2 equals to. So you can give two input files, which is always the twins of the parent sequencing file. And you can also define out and out2 as the output files. This is again, no, I was wrong. It's not a Python, it's a JavaScript again, which will complicate our life a little bit, but not too much. And you can see that it can filter out low complexity and other things as well. But what we want to do is actually something which is here, this one, dedupe, which is in default is equals to f, which is false. So in default, it doesn't do any deduplication. But if we say dedupe equals to t, true, then it will do the deduplication. So let's go up an arrow and say in equals to, And I think it is not working like this, but yeah. So let's put a space here first. And dot dot slash raw data. So I'm going up to the Scratch directory. I'm going into raw data. There is this file underline 1.fq.gz. Okay. The problem is that we have to go back with our cursor and delete this space. I put that space there because then I can use the tab to autocomplete. But what I will do now is that I will just highlight this and copy. If you have the putty and you are using Windows, then if you highlight anything, you can paste it with the right click on your mouse. If you are using Mac, in the Mac terminal, you are highlighting something, you push Command C as copy, and then you can use the Command V. And this is what I will do now. So I will say in2 equals to Command V, and I'll just go back and rewrite this to 2. Okay, so with this, we have the 2 input files, but we don't have the 2 output files yet. We can put those output files in our own directory. So we will fill up the hard drive a little bit, but it's not a big problem. So what we will say is that I want to output the first file into my dedupe underline 1.fq. It won't compress the FASTQ file in default. You can ask it to compress, but it doesn't do it in default, I think. So it will create a simple FASTQ file, and out2 equals to dedupe underline 2.fq. So we are inputting the files from the raw data directory, but we will output the results in our own directory. So from this moment, you will have your FASTQ files in your directory, which you will take forward to the next steps. And the only thing what we have to put here is that function command, which was the dedupe p, which is equals to true, just a t. You can adjust other things like how many threads should be used, I think somewhere, how many memory should be used. I hope it won't use all the threads, because then it will really slow down. We will really slow down each other. But let's see. So I will let you just start. I mean, let me just start it, because maybe there is, oh yeah, of course there is a problem already. The problem is the memory. So we have to probably use the minus xmx flag as well, which will give the maximum memory program can use. I don't know how much memory do we have, so I just check with 3. So we altogether have 24 gigabytes. I think it's okay to use 20, but it means if I'm using 20, then there won't be any more to you. So let me try first, and if it's working, then maybe we can write one by one. Actually, it runs quite fast as far as I remember. 20. Oh, it has to be in. So I will do this, what it says here. 20G. It's running. As far as I see, yeah, it will use all the threads, all 4. Is it only me? Yeah, who is running it? Let's see, how much time do we need? If it's too long, then I can just simply copy my deduplicated files and you. Okay, let me just show you again the command. So this is the command again. If you want to run, I think it's okay to run. I'm not sure if you run it in parallel with each other, then it will be happy. But I think it can work. But we will see. But just try it. Give it a try. So the main problem with this program, because it has to read in all your short reads. It has to have them in the memory at the same time to find the duplicates, to find the similar ones. It requires a lot of memory at the same time.
Sorry.
Yes?
No, I was just going to say, I tried to run it initially before you added in the extra bit at the end with the -xm x20g, and it just kind of came off the terminal. So basically it was saying it was making a comparator, made a comparator, blah, blah, blah. And then it just kind of stopped and came off the terminal. And I now can't get back to the terminal to rerun it.
Try to push Control-C.
Ah, brilliant. Yeah, thank you.
Yeah, that's almost always
My mind went blank.
on a Linux machine. That's one of the magic keys that you can use. It's usually throwing you out from the program. But while it is running, I can explain you what has happened. So as you can see, and as we all already saw from the FastQC, I don't know if I have the FastQC here, but as you remember, we had a problem with duplication levels. So even on the left-hand side, the duplication level has a red X, and there is some kind of duplication here, also here. This is how many duplicated sequencing I think, yeah, we have. So and here we have some duplications. So as you can see here, actually it was quite significant. So we altogether have 5 million. This is a Staph aureus genome, isn't it, Ibrahim? Ibrahim is not here anymore.
I'm sorry.
Are these all Staph aureus genomes? This is the same CC 50 something, 59.
Oh yes, they're all Staph aureus.
Okay, which means it's about 2.5 megabases.
2.5 to 3, yeah, roughly. Yeah.
Okay, so if we are saying 2.5 megabases and we have 5, let's say just simply 5 million reads, that means that we have, and each read is 150 nucleotide long. That means that we have 2 times and 150 times more reads than nucleotides. So we have, on average, we can assume like a 300x coverage, 300 times coverage for this genome at the end. But as you can see from the 5 million, more than 10% was excluded. So only 4,700,400 blah 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 was put in the output, and this is the number of nucleotides. But even this one is way much more than the genome size, as you can see. So this is 700 million, and our genome size is 2.5 million. So we have about 300x coverage here. As far as I see, it is continuously running, and we ran out of time. So what I will do, it seems that we will need a bit more time for all of these topics, just to go through together. I will do some preliminary installations for Thursday, and we can go through together on the one remaining step of the pre-assembly. That will be very fast. I don't know if we have, Marta, do we need to finish at 5 or?
Nope, you can carry on.
I'm just thinking about, because the Flash is actually, it's not just fast because it is called Flash, but it's really quite a fast program. It would be nice to have all of these things in one day, and then we can just do the assembly and the post-assembly on Thursday. So if Rhiannon, are you here with me?
Yep.
Okay, let's just quickly download the Flash. So, oops, Google. And if you Google for Flash and yeah, something like this, Flash and read merge. Otherwise, the Flash will give you a lot of non-specific hits. So this very first one from the Johns Hopkins University, this is what we want to do. And from here, again, just simply copy the precompiled Linux x86-64 binary, not the source package, but the second one, okay? Right click and copy link.
Yep.
Let's go back to our, is your program running now or Clumpify?
It just keeps doing the same thing. It keeps going and then it doesn't like it. I've checked the syntax and nothing seems to be wrong, but it just doesn't seem to like it and just throws me off the terminal every time I run it.
I think it's because someone else maybe was running at the moment. So you can just try a bit later. Okay, just say cd and go back to our main directory and do the usual wget and copy the flash here. This will be much faster. Oh, yes.
Yep.
And again, as you see, it is a tar gz. So we are doing the same as we did before. Tar -xzvf and then flash tar gz.
Hang on, it's saying it's, oh no, it's all right. It's me. I forgot to put a space in. It's all right. Ignore me. Sorry. I'll try again. Sorry.
Okay. It's a much smaller package. It's a very targeted program, only one program, which is called Flash.
Sorry, no. It's saying failed name or service not known, unable to resolve host address. So I don't know whether
maybe there is something wrong. Just try again, wget, and then the quotation marks and just paste the link there again. And close it at the end, of course.
Yeah. No, it's still doing the same thing again.
Okay. Don't mind, I would just copy it there.
Sorry.
I will actually copy the folder there and then you can just use the folder. So I will just.
I know I did something wrong. It's okay. I did something stupid. It's okay.
Okay, don't do anything now because I already.
That's fine. Yeah, sorry. I realized I did something really stupid with it. It's fine.
Okay, then I will remove. And you can do the tar.
Try it.
The tar -xzvf.
It's still not liking it. It says cannot write to flash. No such file or directory. Sorry.
It was me.
Sorry.
Because I'm just doing other things here. Are you in your home directory?
No, I'm back in the, I'm back in my own course.
No, it was my fault. It was my fault. I just did all the by directory. It's okay. It's okay.
Sorry.
I'm really sorry. I just completely removed all your home directories.
Oh, did you?
Yeah, but there shouldn't be any.
Oh yeah, by info. I see.
Sorry.
Well, now we know that we need to be very careful with the directories.
This is the worst. This is the worst command. I mean, if you sudo rm -rf is the worst thing. Okay. Right. I will put everything back there. Okay. Was there anything else? I will, of course, edit this out of the YouTube video. This has never happened. Okay, I just have to do one more thing. CH. Right. Everything is there, and everything has the your right. So if you just go with into your home directory now with the CD and do the tar -xz vf, this one, then it should work now.
Just a moment. So hang on, from the home directory now, right?
Maybe you have to say CD again, because when I deleted the directory, maybe you were just put some.
No, I'm in the bio. It definitely thinks it's in bioinf, of course. It still thinks it's there, so that's okay. But it's not picking. Hang on.
Just say CD.
I'll just change it. Yeah. Okay.
And say pwd, just to be sure that you are in your home directory.
Yeah. Home bioinf. Yeah. Yep.
So now you can do the tar minus. I'm putting it here on my screen. Minus xzvf.
Yep.
And it's only on compressing 5 things.
Okay.
Copying news, readme, and the Flash program itself.
It's not finding, when I do the tab to try and find that file, it's not finding it.
Are you using the capital F?
Yeah. Hang on.
It is there. I can see it. If you say ls, can you see
Yeah,
the?
yeah, it's definitely there. So I don't know why it's not finding it. I'll just try it again.
Don't forget the space.
Yeah. Oh, there, it's found it now. Yeah, that's fine.
Okay, let's go back to our Scratch directory.
Okay.
To your own. Now everyone can do this. So let's first run the Flash, which is in our home directory. So for you, it's home/home/bioinf. For me, it is Ubuntu, and then the Flash directory. Strange, it doesn't, I don't have it now. Okay, nice. I also managed to delete it from my own directory, I think. Oh yeah, because I wanted to show you. I think that was the reason. Okay, so scratch pair / my own directory and run home slash Ubuntu for me slash flash. So this is a case when you only get a very short help on usage, but it also says that if you say minus minus help, then you will have a much more complete help. But actually, we don't really need anything else now, because as you can see, the basic usage is you say flash, and then you say you will give the first and the second FASTQ file for the program. So what you have to do is just go up with the up arrow, and you have your files already here. The deduplicated 1 and the deduplicated 2. And that's all. And if this is run with all the default, all these default settings, then you will get back a few extra files here in your directory. This is way much faster. And it's only using one CPU, I think, in default. So even if we are running it all together, yeah, we are running it again together, it won't really slow down significantly. So what does it do? What did it do? As you can see, this is the number of read pairs that were read in, and out of this, about, okay, it's actually exactly 12.39% was combined. The combined means that they were overlapping in some length in the middle. As you know, the next generation sequencing is always, when you have the two pairs, they are always facing to each other. So the ends can overlap and can be homologous. If you now say ls minus ltr, we use ls minus l quite often. ls minus l is giving you the detailed list of your folder content. The ltr is giving you the same thing, but it is ordered by the creation time, and the new files are always done at the bottom. So it is a very useful command if you have quite a lot of files in your folder and you just want to see what were the new files that were created. So the three main files which we will use on Thursday for the assembly, and these are the input files to the assembly. So you have two not combined files. So these are exactly the same as the dedup1 and dedup2, but all those reads that were able to be combined, so that were merged, they are not in these FASTQ files anymore. This is why it is a bit smaller. So as you can see now, because they are not gzipped, you can see the size of the file. This is like 8. If you say H, then you can also see it in a human readable form. So these are like 700 megabytes, which went down to 600, or a bit less than 700 megabytes each file. And those reads that were merged, they are all in this one as single end reads. You also have these two extra files where you can see the distribution of the merged ones. So if you just simply say less out.histogram, I don't know which one is nicer. I think the histogram is nicer. Then you can see here the size of the merged read. And as you can see, the smallest one was 202 nucleotides. And then as you go down, you will see more and more asterisks. So the longest one is 290. We are doing 150 base pair long parent sequencing. So this one means that they had 10 base pairs in their end, which was overlapping. Next time when we will do the assembly, I will give you a bit more options how to make this kind of read merging a bit more strict. I don't really like letting just 10 nucleotides there. I like having at least 30 nucleotides in the middle to be completely the same. You can use the Q to Q it. I had a question here. Yes, I can show you. So this was the program. You call it by going to the whole path. So /home/bioinfo and in the flash directory, the flash program, and then you just give your two deduplicated FASTQ files, which was created by the Clumpify in the previous thing.
Thank you.
Okay. Okay. So what we will go forward is I will show you a few optimization steps for the flash, because the flash should be used every time. So it's good if you have it in the most optimal way. If you use it in the most optimal way, and then we will go to the parameterization of the assembly, but we won't do. I will check how long is the assembly for this one, but I think it's too long to do it for all of us. So maybe I will just show you how to do it, and then I will give you the results as well. Or actually, what I can do, I can send you. No. Yes, I will show you how to do it, and then you can practice later, even in your own data. And then we will do the post assembly steps, which is much more interesting, especially biology, much more interesting, and also much faster, because we only have to work with a FASTA file, a few million bases, not 700 million. So there is one thing. I think it would be very nice if you have any of your own data, just copy it to the server. If you have any sequencing files, I don't tell you to copy hundreds of colony sequencings here, because we don't have that much of space, as you know. So if you say df minus age, we already filled up 7% of the scratch directory, and it's only one sequencing yet. So we have to try not to fill up the whole space, but if you have a few, and if you want to try on your own sequencings, just feel free to do it. You have your programs now. You know how to use these pre-assembly steps, and just try to check. And actually, there was a question last week, and this is the closing remarks now, well over time, from Kota. What are those things that you can check from all of these outputs? So if I go back to the Clumpify, if you see an extremely high percentage here. So what we saw here is about 10% of the reads was excluded, which is okay. I think 10% of duplicates is an acceptable level. But if you started with a very low amount of DNA and you thought that, okay, just by amplifying with PCR, I can have the required amount of DNA for library prep. But here you see that 80% of your reads were excluded because of the duplicates. Then maybe it's better to go back and reculture and re-extract your DNA. So that's already a point where you can have an idea of your sequencing. The other thing is here. So of course, when you are doing your library and you are sharing your DNA, you are trying to get a well-defined library size, but there, I mean, which you also check back probably with a bioanalyzer. But there are cases when something goes wrong, and there are too many very short fragments. So if you, for example, aim to a 400 base pair library size, which means that your 150 base pair reads will probably not overlap in the middle, or just a very small amount of them, something like here. But I think it was a bit larger, this library. And you see that 80 or 90% of your reads were merged. Then there is again something wrong. Then you have to be suspicious that maybe your library size wasn't what you really wanted, or there was something wrong in there. And of course, always check the fastqc, which we had here, to see if everything is green. If not, probably there is a reason why it is not. You can always go to the fastqc documentation. What does it mean at the per base sequence content? I can imagine that this sequencing has the indexing or something at the beginning. I haven't checked it, but this is very, very, very strange what we see here. It's not an adapter. That's what we know. Okay, so that was everything for today. If there is any question, there is a time for one short question. And really sorry for being this late. But I hope you learned a lot, and I really hope you will have the chance and time to do some practice until Thursday, and then we will continue with the further steps. Is it okay for everyone?
Yeah, great. Thank you.
Thanks very much then. Have a nice afternoon and evening, and see you all on